Hello everyone. Welcome to the magnetic field lab. Okay, so we're going to measure the magnetic field of a short solenoid along the axes of the solenoid as a function of the distance from the center of the solenoid. Okay, and find out how the magnetic field varies as a function of distance. So this is our z-axis. Okay, the z-axis is the center, basically the center of the solenoid. The solenoid has a radius r. Okay, and it has a length. Okay, this one has a finite length, which is short. Okay, so we're going to approximate the magnetic field from the solenoid by treating it as if all these windings were at the x equals 0 or z equals 0 here. Okay, so the bottom line is we can find the exact solution, which we'll do later in the analysis for a finite length solenoid here, and compare it to our approximation and see how it works. But for right now, let me just explain how this apparatus works. Okay, so the magnetic field will be measured with this secondary coil right here, which is basically hooked up to an oscilloscope. Okay, on channel 2 right here. There is no voltage attached to this solenoid whatsoever, and it measures the magnetic flux passing through the center of it. Okay, so if you look at the center of this coil right here, there's a flux passing through that, and a changing flux will induce a voltage on this solenoid, okay, which I can measure across a resistor right here. So the voltage on this solenoid will create an EMF on the resistor, which makes an electric current and completes the circuit, and I can use my oscilloscope to just measure the voltage coming off of there. And if you look at my oscilloscope here, okay, if you look at my oscilloscope, this is the signal that's attached to the pickup coil. As I move the pickup coil closer to the coil, you can see that the voltage on the pickup coil increases as you get closer and gets weaker as you get away. Okay, so that voltage is proportional to the flux of the magnetic field passing through the pickup coil. Okay, so here is, if you look at your lab sheet here, here's a schematic of what I just did. The magnetic field is passing through the center of the pickup coil, and I have my oscilloscope attached to the output of the pickup coil, and I'm measuring the peak voltage. Okay, so you're wondering why that the magnetic field is not constant. Well, that's because the current is not constant. I'm injecting a sine wave into the short solenoid. Okay, so the current is varying as a function of time, and it has a peak current. And as you know from our calculations last time, the magnetic field depends on the current, the radius of the solenoid, and the number of windings, okay, of the solenoid. Okay, and this is the magnetic field at the center of the solenoid. A distance z from the solenoid, the magnetic field varies by this formula. Okay, it varies by the distance from the solenoid and the radius of the solenoid and the current and the number of current loops. Okay, so as I move farther away from the solenoid, the magnetic field gets weaker. Okay, or the peak magnetic field. And since the current, both of these things depend on the current, and the current is fluctuating with time, then the magnetic field should fluctuate with time. So if the current is fluctuating with time and the magnetic field is fluctuating with time, then the voltage on the pickup coil will fluctuate with time. Okay, so let's look at Faraday's law. The voltage can be found by Faraday's law, which we're going to calculate next week. Okay, and Faraday's law basically says that the voltage is proportional to the changing flux through the number of current loops. Okay, well, it's equal to the number of current loops times the changing flux divided by the time. Okay, so the flux is, as you know from electrostatics, is the field passing through a given area. So the flux that passes through the area of the pickup coil, okay, which is this area right here. Okay, here's the front of the pickup coil. So the amount of magnetic field that passes through that area is the flux. Okay, so we just multiply the magnetic field times the flux, and the changing flux is equal to the changing magnetic field times the area. Okay, so the bottom line is we can find the voltage on the pickup coil from Faraday's law, but we don't have to do that because we can calibrate our puck because we know what the peak magnetic field should be if we know the current. Okay, we can measure the radius of the solenoid. Okay, of the solenoid here. We can measure that radius, and we can measure the current going through it, and we can count the number of windings on the coil as well. So. And then if we just plug those into this formula right here, and we'll know what the magnetic field is at the center. Okay, so the magnetic field at the center of this can be calculated from this. So we get the I can measure the current passing through this coil. I can measure the current passing through this coil from this setup right here. Okay, so I have channel 2 of the oscilloscope hooked up to our pickup coil, which is our magnetic field probe, and then this other channel is hooked up to the short solenoid in this manner. Okay, so the signal generator sends the current through the short solenoid and goes back through this 100 ohm resistor. Okay, this side of the resistor is grounded. Okay, and then we put channel 1 and measure the voltage, or the peak voltage, across the resistor right here. And if we know the peak voltage and the resistance, we can use Ohm's law and find the peak current. Okay, so that's exactly what we're doing here. Okay, so I'm going to take the pickup coil right now. Let me show you what it looks like on the oscilloscope. Here's channel 1. Okay, this is the signal across that resistor right here. So I have the signal coming out of the signal generator right here. Okay, here's the signal coming out of the signal generator, goes into one side of the coil. Okay, goes into one side of the coil and comes out of the other side of the resistor, which is grounded. Okay, then the signal to the oscilloscope, channel 1, is connected to one side of the resistor here and goes to ground on the other side. So this is the voltage on the resistor. Okay, so if I want to find the current going through that resistor, I just measure that voltage, and that voltage happens to be about, well, let's zero it. Let's zero this. So this is channel 1 right now. Happens to be just about 5 volts peak. Okay, so we got 5 volts peak going across that resistor right now. So there's 5 volts peak going across that resistor, and so that means that the current going through that is going to be 50 milliamps. Okay, the current flowing through that is 50 50 milliamps, okay? 5 divided by 100, yes, that will be 50 milliamps of current going through the resistor. The peak current is 50 milliamps, okay? So now we have a way to calibrate. We have a way to calibrate the scope, okay? Or calibrate our probe, okay? So I'm going to stop this video, and then the next video will be to show you how we're going to calibrate our probe, okay?